Good evening, welcome to Real Learning Center. So, we are going to basically today continue from where we left. We have actually done two classes till now. In the first class, we kind of learned some concepts in electrostatics. In the second class, we continued and learned a little more. For example, in the first class, we learned what is electric charge. The electric charge is the fundamental thing in electrostatics. Electrostatics. Yes, electrostatics means electric charge is standing. Now I am telling you the meaning of electrostatics. Electrostatics means static electric charge. So means charge is not moving, it's standing. That is called electrostatics. Now in our case we can see that we are only talking always about electric charge standing, not moving. If it moves, it becomes electric current. So electrostatics is about charges standing. And here we learned about when a charge is standing, lot of properties of charges we studied, and we also studied the electric field. What is the meaning of electric field? Which is around the charge. It is nothing but the electric force. Yes, the force on a unit positive charge. We learned that electric field. We got some idea. We also learned about electric flux, which is electric field into the area. Okay, that we found out. That is called electric flux. And we even studied the concept of Gauss law and how to use the Gauss law in some applications. That also we studied. So these four we have finished. Yeah. Now we are left with some concept called as electric dipole. What is the meaning of electric dipole? That we need to study. And another important thing is electric potential. In fact, if in your textbook, if you see in your NCERT textbook, there are two chapters. In one chapter you have electric charge and electric fields, and also about electric dipole there. And in the second chapter, it is electrostatic potential and capacitors. They have mixed basically electrostatic potential and capacitor in the second chapter. Whereas electrostatic potential is one of the most important aspects of the electric charges and electric field itself. So I would like to talk about electric potential or electrostatic potential first, okay, and give some idea about that. And then I will talk about electric dipole. The electric dipole, when I talk, we will actually try to talk about something which is in the first chapter and in the second chapter. Both we will talk. Okay. Potential is of course in the second chapter. But if we finish first and second both chapters is electrostatics. So today we will first introduce what is the meaning of electric potential. So as I promised you, mostly I will be talking about conceptual understanding and a bit of mathematical interpretation. I will not be doing every derivation in very detail. Wherever needed, I will do. But lot of derivations we can actually pick from the textbook or the notes. Always. Now, so what is the meaning of electric potential? So before we talk about electric potential, we shall try to understand what is the meaning of potential energy. Potential energy is not only in the context of electricity. It is not only about electrostatics. Potential energy is used in other places also. The previous year, that is in the first PUC, you would have studied about potential energy in the context of gravitation. What is the gravitational potential? You must have studied about that. Potential energy we have studied in the context of a spring also. Potential energy of a spring. So generally, one observation is that wherever you see there is there is some force, then potential energy is basically there in that. But you also understand that in some forces, in certain kinds of forces, there is no potential. For example, friction is a force. In the case of a frictional force, nobody talks about frictional potential energy. There is nothing like that. So, in some forces, potential energy is available, possible. We talk about potential energy. In certain forces, we don't. So, the reason basically is the forces which are whatever we call conservative force. Potential energy is only there in the conservative force. Potential energy is not there in the non-conservative. What is the meaning of this conservative force? So conservative force is basically where the work done is independent of the path. That means if you are lifting something from some height in another height, basically there is a certain amount of potential energy that it acquires because you have lifted it. Okay. mgh means h is small here, h is high here. So there is a difference. So that much of extra potential energy is one acquired. But even if you take it this way or this way, any way you take, if you are actually having this height and this height, the difference in the height will tell us what is the potential energy. It doesn't depend on which path you take. Yeah, the work done is same irrespective of whichever path you take. So potential energy, that's why is possible. Whereas in the case of frictional force, work done in different paths are not. Yeah, on a road, you are going to go between 2 points on the road. To go straight, you will be basically spending less fuel. If you go on some other path, you will be spending more fuel, you will be spending more energy. So work done is more. So friction, either you go this way or this way, friction is only going to basically be consuming energy. Whereas in this case, if I take it up, it consumes energy, and while coming down, it comes on its own, it gives energy. Yeah. In one direction, it consumes energy, in the other direction, it gives energy. In such scenario, we call it as conservative, and that's when potential energy can be defined. Okay. So that is the first understanding of what is potential energy. Potential energy is a very simple concept. If you take, for example, a spring is there and some mass on it there. Okay. If you actually pull the spring in this direction and pull it up to this point, your mass is pulled up to this point. Then when you hold it, you say that it has. If the mass is here, where you don't have to hold it, you leave it, it will be staying there only. There is no potential. But if you are going to pull it here and hold it here, it has potential there. Because the moment you leave it, it will start moving. If you leave it, it will start moving. That's a good indication that it has potential there. Here, if you leave it, it won't move. So it doesn't have potential. Now, if you push it here to this side, you push it here to this side, even then it would have potential. Why? Because if you push it and keep it like this, if you leave it, it will start moving. If it starts moving, that means it has potential. Okay, that is the way to understand whether a potential energy is there or not. So even if you pull it, it will have potential energy. Even if you push it, it will have potential. The spring has potential energy, but it can store potential. It can store energy. So that's what we say potential. Stored energy. The moment you leave it, it will get converted into kinetic energy. So whereas if you look at, for example, from the surface of the earth, let's say you are going to lift something from here to here. Let's say you take a book and lift it, a box. Okay. So when you take it up here, you leave it, it will fall. That means the same scenario as this. If you leave your hand, it will fall. So it will start moving. That means it has potential energy. So that is how you know something has potential energy or not. So wherever there is a force that is acting on something and you are holding against that, then it will have a certain potential. Okay. So now when we talk about electric charges, it is the same scenario because we know that electric charges, that means basically positive charges and negative charges. If there are two positive charges, they repel. If there are two negative charges, they repel. Positive and attractive negative charges, they attract. So these charges will have basically attraction and represent force, and these forces are will make sure that there is potential energy. So if I want to write down, for example, one charge here, let us say I have a charge of some 2 coulombs or something, plus charge, yeah, let's say 3, and if I keep another charge here, that also plus charge, let's say 2 coulombs. Yeah. Now this charge I will keep it in such a way that it is basically fixed. I take that small charged ball and stick it somewhere. So and this charge I will keep it on the table somewhere. This is my table. I'll keep it here. Now what happens is that if I want to keep it here, this charge will, you have to hold it. If you don't hold it, this charge will go away because it is repelled. Correct? This will be the direction which it will go away. So if you want to hold it here, that means basically you are holding it here, it has potential energy. That's how you define how it has potential. Even if you take a negative charge, let's say I will take a negative charge, negative minus 2, I'll keep it on the table. Yeah. This one is anyway fixed. So this one, so let's say this is not there, only on this one. So in that case, what happens is this charge will be attracted, correct? Will be attracted. Because of that, if you hold it here and leave it, it will go towards it. So this is a natural tendency for it. So whether this one or this one, both of them have what we call potential energy. When you keep it there is a potential energy. So what is the amount of potential energy? Do we have a number for this? How do you know how much is the potential energy? How to define that? That's where we start working in mathematics and physics. So you will do some interesting math to get the value. Now we will actually make some very formal statement saying that potential energy due to a point charge. Potential energy due to a point charge at a point P. Like that we give some formal statements. Okay. But please understand that what we are trying to do is one simple thing. We are trying to see when I actually keep it here, I have put some effort to keep it there. So whatever effort I have put there to keep it there, that is stored as energy. That's all. That is called potential. So think about this. Okay, what have I done? I have actually taken somewhere there my 2 coulombs were there. Okay. I'm going to bring it here and keep it. So further some effort I have. So now think about this very idealistically. So in the physics generally we think about effort actually means actual real practical effort we don't take. We take as a mathematically we calculate hoping that everything else is not there. Only one thing is there. Gravitation is not there. All that we take. So it's a very idealistic situation. So that means basically what happens is this one charge you are taking from somewhere and bringing it. So what is the one which is opposing that? This is the only charge that exists on this universe. You are explaining. This charge is pushing it away. I am trying to hold it here and bring it here. This charge is pushing it away. But still I am bringing it. So total I am putting some effort for that. That total effort is called the work. Work done. From where are we bringing this? From somewhere very far. From very far we are bringing. So we'll say work done in bringing the charge from very far. From very far Let's call this point as P. I'll call this point as P and I'll call this point as, let's say, A. So from somewhere I am bringing one charge and putting it here. From very far I will use a very idealistic name for that. Very far means instead of that I can write it as infinity. Very far means from infinity to that point. So that is the definition. This is here the definition. If you see, work done in bringing the charge from infinity to this point P is the potential. Correct? That is nothing but the potential energy. That is the definition. Do not by heart the definition. You understand it. What I am saying is that what is the potential energy? This is how you have to store in your head. Okay. So how do you know there is potential energy somewhere or not? You keep some charges, leave it there. If it starts moving, that means there is a potential. Correct? That means you are putting some effort in putting it there. So how to measure that? That is the next. To measure that, you have to bring it from infinity. That means very far to that point. Whatever you have effort you have put for that, that is nothing but the total energy that is stored. That is the amount of potential. That is the definition. How do I calculate that? We will see. How to calculate what is the energy, what is the work done in moving from infinity to that point, we will see. But that is the definition. Work done in bringing the charge from very far, that is infinity, to this point P is the potential energy. Okay. So this is the potential energy at point P. Now, this potential energy when you are talking about, it is not just for this particular charge. Okay, it is for any charge. Here also you can keep any charge. Here also you can keep any charge. Okay. Depends on basically on both the charges. The amount of work you have to do depends on both the charges because you are basically opposed by the force. Correct? That force depends on how much charge here. Force we know is Coulomb's law. Q1 Q2 by R square. This is both the charges. So hence, what we need to understand is that the potential energy is defining something about both the charges and their distance. Potential energy at this point for this charge, okay, with respect to the another charge. So there are so many variables. There are three variables. Okay, one is how much is this charge. Second is how much is this charge. The third is how much is the distance between. All of them are there. So there is a new word that we are going to use, which is called, instead of potential energy, we'll just use potential. Electrostatic potential or electric potential. So we'll use this word potential. Potential is also energy one, but on a unit positive charge. That means if I have to here in this place I can keep whatever charge we want, but here I have to keep plus one unit positive charge. If I keep unit positive charge and do the same experiment of bringing it from infinity to this point, whatever the work is done, that work is stored in the energy as energy, and it is basically called potential, electric potential. Electric potential is the name for the potential energy for one charge. Like this basically. I mean, we always want to find out for per one of them how much it is. The rate, price, like what we say is generally even electric force per unit positive charge is called electric field. Electric field is not anything other than the force, just a force, but it is for a one charge. Charge value one, correct? So energy for one. So we are interested in for one of them. Why are we interested in that? Because once you know for one, you can calculate for anything. Just multiply. So if you take for example, the charge here is, let us say, Q1. P plus 2 minus 2 minus 3 minus 3, whatever 3.5, whatever you can write Q1. Then if you know for 1, so I will call the electric potential as V, V at point. So V at point P into that Q1 if you do, you will get the electric potential. Electric potential is given as U at point. So look at some of the definitions, some of the words that we use. This is electric potential energy. This is potential energy. This is potential. Potential is V. Potential energy is. So this basically is Q1 is the charge that is kept. So what is the meaning of this? It is like this. If you know the cost of one banana, you can calculate the cost of 10 bananas or 12 bananas, whatever it is. So V is the cost of one banana. Q is the number of bananas. So total cost is nothing but cost of one banana into number of bananas for 10 bananas. So that's the simple thing that we do. Most of the work is like that only. We give different complicated names. So ultimately we are doing such simple things. So you understood basically potential energy is nothing but potential into the charge that you are going to keep. So charge that you are going to keep it here is already part of the VP. Okay, VP is because of this. If you have a higher value here, VP at this point, we are not, look at this, what we are doing. We are trying to find out the potential energy at this point because of some charge. It is a property of this charge and this distance. So there are 2 points here. One is how much charge is kept and how far is this kept. So potential is going to tell us both. Yeah. So potential is about how much is the value of the potential at this point due to the fact that at certain distance some charge is kept. How much is kept? If you kept a higher charge, this potential will be higher. Okay. But if you want to find the potential difference, potential energy at this point, then whatever charge you are going to put here, you have to multiply with the potential. Okay. So this is how we basically work with using potential and potential. So that is basically an understanding of what potential energy is. Now, this electric potential, what we call electric potential, is a scalar quantity. Electric potential is a scalar quantity. Scalar quantity means what? It doesn't have a direction because you have put some effort bringing from infinity to that point. Okay. So that effort is basically in terms of joules, that much energy you are spending. It is not having any direction. So, but it has, of course, it has positive and negative. Scalars can have, like temperature can have positive and negative. Scalars can have positive and negative. That means probably has put some effort uh, from bringing them from here to here, then it's called positive. If you have not put effort, or if you have put effort in the opposite direction, if you are holding it back so that it won't come, then that is called negative effort. If your effort is in the opposite direction of the movement, if your force is in the opposite direction of the movement, then the effort that you have put, the work done is negative. That's basically your definition of effort. So this value can be either positive or negative, but it cannot be having any direction. It's just some value. So that's what is basically electrostatic potential, and given by the word B, in the letter V, V at any point, and the units for this, units for this is given by a unit called volts. We write it as just V. Okay. Volt is the name of the scientist. We use it for using the potential. But you know that it's ultimately nothing but potential energy per unit charge. Potential energy is joules. Okay. Joules per coulomb. Okay. A volt is nothing but joules per coulomb. Potential energy per unit charge, joules per coulomb is. So this is the way to basically understand the potential energy. Now we will have a way to compute the potential energy for a unit, for a point charge. So there is a point charge here, correct? So how to compute it? How to compute how much, how much of the energy is spent from here to here? That requires basically integration and all that. Okay. So I am not going to spend too much of time explaining you how to do the integration. However, I will explain the basic idea behind doing calculating. Okay. So let me explain the potential energy due to a point charge. Potential, electrostatic potential due to a point potential due to a point. So let's have a point charge. This is plus Q, but a point charge is plus. Now I am going to keep here at point 3 a charge that is 1. Okay, I said unit positive charge plus 1. I'm going to keep it as plus. This is Q. Q can be any plus. So at some distance, let's call it as the distance from here to here is, let's say, capital R. Okay. So I'm going to put this R as a position vector by basically writing an arrow here. You can do. Now, to be able to keep it here, this charge, you have to put some effort. What did you do? You brought it from somewhere infinity and kept it. Okay. So that means I'm going to write here, this is my infinity, just for the sake of argument. The infinity is very far. So it's coming from here. Coming from here. This is infinity. It's keeping on coming from somewhere infinity, like in this sense. So what is the effort it's having? So if you want to find out that, the problem is a very interesting problem here. We'll tell you a little bit more about why we need to do integration. So it will, let us say, come up to this point. Just come to this point. Right? It is coming from infinity. Slowly we are bringing. Very slowly we are. So we are bringing such that there is no acceleration. If you give acceleration, then kinetic energy also will increase. You don't want to increase the kinetic energy. Just come at constant velocity. Now at this point, basically the distance from here is small r. Okay, so I'll just write it as small r. So let's say this is another point. Okay, I'll call it as this point as A and this point as B. Between A to B, you have a small difference of length. I will call it as dr. Okay. Now, if you are bringing it from there, at this point, you are pushing. So you are putting some effort, some force, okay, to bring it. Okay. How much force you are putting? You have to understand that. That force that you are putting on this must be equal or more than the force with which it is pushing. Okay. The force because of the repulsion force. So I will call it as electrostatic force. It has a force Fe, I will call it electrostatic. Electrostatic force is defined by the Coulomb force. So you can even call it as Coulomb. So it is pushing by Coulomb force, and this direction you are basically coming in the by yourself pushing. So if these two, if F is more than Fc, then only it will come this way. Correct? So in this case, what we are taking is F is equal to Fc. If F is equal to Fc, then what happens? There is no acceleration. It will come at constant velocity. Okay. So we have to take F is equal to F, but in the opposite direction. So F is equal to minus F. So that is the force that we are using here. But as you come nearer and nearer and nearer, okay, the value of Fc will keep changing. It's not going to be same. You come nearer. What is the value of Fc? Fc is given by 1 by 4 pi epsilon naught into Q into 1 divided by R square. Correct? Q1, Q2 divided by 4 pi epsilon naught R square. That is the force. Electric charge force we discussed about Coulomb's law. That is what is this. Now, if Q into Q divided by R square, there, Q into 1 by R square. There. Now, this Fc as R changes, when it becomes smaller and smaller, F value will increase. So, at this point, whatever is there at this point, at this point, at this point, different values of F has to be given. F is not a constant force. F is a variable force, and F is dependent on R, the function of R. Correct? So, we say that at least we'll assume that if it is a very small distance, dr, very small, tending to 0, very small distance, during that point, we'll assume that F is constant, not changing. We'll just assume. Because dr is very small means we can assume. So, work done from here to here, we'll say, work done, or the effort put from moving, work done in moving from B to A, B to A, okay, is equal to, I will call it as dW, that is small amount, little bit of, is given by, okay, that F, it is a function of R, okay, dot dr. The definition of work, remember last year, work is defined as the force dot distance, F dot dr. Now, this F dot dr, you take for example, the F is in which direction? This direction. Dr also is in this direction. Okay. So, basically both of them are in the same direction. The angle between them is 0. So, we can simply write it as F into dr. However, this F can be also written as minus F. So, we have already said that it is equal to the and opposite to the Coulomb force. So, this can be written as minus Fc. This is the work done in moving it from here to here. Right? So, please understand this. This is how we formulate lots of problems in physics. If you understand this, you will be able to do a lot of nice physics. Okay? So, we are trying to find out how do we formulate the integration. We will basically find for a piece, for one piece how much is the work. For the next piece from let us say A to some other point, some amount of new work, some other work is done. So, another piece from before this, one more amount of work is done. Now, all these work, each work is different. Why is it different? F is going to be different. Even though you keep the dr same, small piece only you are taking from here. All these pieces, the distance dr may be same, but F is different in each case. So, when you add all of them, this plus this plus this effort from each one of them, if you add, you will get the total effort. So, it's like a addition. So, for addition you can use sigma if it is a discrete addition, separate addition. But it's a continuous addition. Continuous addition means that dr is tending to 0. This is my micro level, very small. So, it's a whole long one, continuously changing. That is when you need integration. Integration is nothing but addition. So, it's a way of doing addition. Newton found out that you can do a very interesting kind of addition using integration. So, for that addition, we are going to write here integral of and integral of. So where to where integration, from where to where you are coming? You are coming from infinity to this point. So I am going to write infinity is the highest distance. Capital R is the distance to the point. So infinity to point. Now once you get that, okay, you can write here infinity to point P, and right here minus outside, and what is FC? 1 by 4 pi epsilon naught into Q divided by R square into dr. So think about it, lots of things are constants. So what are the constant things here? See here, lots of things are, what are the constant? Constant things are 1 by 4 pi epsilon naught and Q, Q is a constant, and only rho to P, you have R to the power of minus 2 dr, R to the power of minus 2 dr. So whatever is in the denominator as R square has become R to the power of minus 2 in the numerator. When you integrate it, R power n, if you integrate, you get R power n plus 1 divided by n plus 1. N in this case is minus 2. So I will write it as Q divided by 4 pi epsilon naught into R power minus 2 plus 1 by minus 2 plus 1. And then we have to apply the limit infinity to P. Okay, so we are going in some direction. This is the integration. Don't lose what we are trying to do. We are only trying to find out the effort going from here, because that will tell us what is the potential at this point. Okay. So that effort to be able to calculate that effort, we are basically going through a certain step by step method that Newton has taught us about this integration. Okay. So it is not just learning about potential, it is about learning this method also important for us to do something, do lots of good problems. So that's why I'm spending some time to explain this. Now, if you see here, this is nothing but minus 2 plus 1 is minus 1. So that minus 1, take it outside with this minus, it will become plus. So Q divided by 4 pi epsilon naught will be there. Okay, that has become positive. Okay. Now R power minus 1. R power minus 1 is 1 by R from 0 to capital R. The infinity to capital R. Sorry, I have to use here capital R. P is the name of the point, but it is actually distance wise capital R. So this can be written as 1 by R minus 1 by infinity. That's how you substitute for a definite integral. I hope they have covered that in your class, but if they have not covered, that will be covered in the math, where you will do a definite integral 1 by capital R minus 1 by infinity. Okay. First upper limit and then lower, and then you have to subtract 1 by capital R minus 1 by infinity. 1 by infinity is 0. 1 by capital R only will be. This will become basically Q divided by 4 pi epsilon naught capital R. That is the answer. What is that? That is the total work done. And total work done is nothing but the potential at point. So what we got is potential at point P is equal to Q divided by 4 pi epsilon naught R. Q divided by 4 pi epsilon naught R. So just remember what you had calculated for E, the Coulomb's law. For E we had E divided equal to Q divided by 4 pi epsilon naught R square, small r or capital R, depending on how much. So for E it is R square, for V it is R. So that is a major difference. So if you know E, you can remember V also. So E is something which is basically inversely proportional to R square, and V is inversely proportional to R. This is for what? This is only for electrostatics of electrostatic potential due to a point charge. This is due to point charge only. Okay. So we can now see that we have kind of derived electrostatic potential for a point charge for a one single point charge, for basically to use by using the concept of work done in moving from infinity to that point. So we have integrated that. So we have understood how to integrate, why to do integrate, all that. Okay. Now ultimately we have got these formulas. So this formula we already got as electric field. This formula we got as potential. Okay. So but here this is vector and this is a scale. So we'll just show once how does it really, what does it really mean by this? So because in physics mostly whenever you after the derivation, if you go away, then you will not understand anything. You need to basically interpret it, stay there for some time and understand it. And yeah. So what we will do is we will try to understand what it means by this. So in both cases, q by 4 pi epsilon naught is also is in both cases it is there. Correct? Only difference is one of them is 1 by r, other one is 1 by r. So if you see, for example, I will call this q by 4 pi epsilon naught. For a particular charge, I will keep some charge. Okay, I will keep it charge, some charge. So let's say q by 4 pi epsilon naught is equal to, I calculate everything and I will give it some value, some constant value. Okay, let's call it as some value. Let's say 0.25, some value. I don't care, some value. So divided by r. This is divided by r. Okay. So if you take this point here, and I am going to basically take one graph here, r, and I am going to plot. I am going to plot E also and V also at some point. So let's say if I want to plot V at a distance of 1 meter and E at a distance of 1 meter. Carefully see, this is nothing but 1 by 1. This is also nothing but 1 by 1 square, both of 1 okay, at a distance of 1 meter, at 1 meter. Okay. Both of them, both E and V. So I'll plot E using one color and V using another color. This is, so let's say assume that this is 1. This is E. Okay. This color is, and V also 1. This is also 1. Okay. This is V. Both are on top of each. Now assume that I am going to double the radius. So I am going to make the radius instead of 1, it will become basically 2. So when you make it 2, okay, so point 2, so sorry, first I took 1. 1 means this is point 2. So 0.25 divided by 1 is point. This I took example as 0.2. 0.25 divided by 1 as 0.2. Here 0.25 divided by 1 square as 0.2. Now I am going to take this one as r is equal to first I took r is equal to 1. Now r is equal to 2. Okay. So if r is equal, so let's call it as small r. So if r is equal to 2, and if this also let's If R is equal to 2, now what happens? This is 0.25 divided by 2. 0.25 divided by 2 is half of 0.25. It is 0.125. Okay, so that is basically right. So this is nothing but 0.125, and at this point, at point 2 here, value is the value of B is okay. What is the value of basically E? This one is 2 square is 4. So 0.2 by 4. 0.25 divided by 4 is 0.065. Correct? So this is 0.125 divided by 12.5, 6.25. Correct? Okay. 0.065. So the value of this one. So this is E. If you become R is equal to 3 or 4 somewhere, okay, go here again. The E will also decrease and R will also decrease, but R will decrease less. So it will actually go like this, R. Whereas E will go even more steep. So generally what happens is that because there is R square here, E actually gets lesser and lesser much faster. Okay, as you go further and further, E becomes very, very less. Whereas in this case, this will become also less, but not as much. Okay. So this is that is why proportional to inverse square. This is proportional to just R. Okay. So E and R, E and V are similarly inversely proportional, but it is inversely proportional to R. This is inversely proportional to R. That's the difference. So this just to give an idea of how E and V changes as the potential changes. Now that is giving you a basic understanding of what is the meaning of a potential and what is the meaning of a potential energy. So once you understand what is potential and potential energy, then see you have now got very good understanding of several things. What is the meaning of it? See, that's all. Understanding electrostatics actually means understanding electric charge and electric force, which is basically between the charges, electric field, electric flux, Gauss law, electric potential. This much if you know, you kind of got the whole understanding of electrostatics. Now you have to use these four things to see in various scenarios what will happen. Like for example, instead of one charge, if you keep multiple charges, what will happen to electric field? What will happen to electric? And if you keep in an electric field one more charge, what will happen? And if you, for example, keep two charges very near to each other, we call it as electric dipole. What will happen? So all that, how is the electric dipole working in terms of, so instead of keeping one charge and finding out the electric potential due to that, you keep one electric dipole and see this. I have not yet explained you the dipole, but I am saying that now almost it is all acrobatics. You are going to do some nice circus to figure out other things. But basic concepts are only this. Okay. So I am going to take the next class and explain to you clearly about what is an electric dipole and what is the electric field due to dipole, electric potential due to dipole. After saying that, I will also talk about what is the meaning of electrostatics of conductor. To actually go into the electrostatics, what happens in a conductor? It's a very interesting area. Till now, we have never talked about conductors and insulators. So we'll talk about that. And finally, we will get into concept of capacitors. Okay. That will be done in the next class. And I hope this has given you some understanding of electrostatic potential.